To get the correctness and speed gains for gesture recognition in my project, I chose BlazePalm for hand tracking, optimised from its baseline. First, I shrank the graph bundles down, performed stability and acquisition, and then I bind the classifier. Finally, this is all passed into a capability registry, which runs on device. What does BlazePalm actually do? It balances gesture, subject, handedness, crop scale, rotation, motion blur, lighting, partial occlusions, edge truncation, and low confidence recovery. Only once all of that is done can a classifier process landmarks. Knowing all of that, I needed to perform surgery on BlazePalm. In my original video explainer, I referred to this as dismantling it. This happened roughly in the following steps. I shrank the graph bundles down without sacrificing quality. BlazePalm used the Torch CPU around 230 milliseconds. I wanted to reduce the average mean to a complete forward pass of the vision encoder. This is the backbone responsible for taking the raw image from the camera and turning it into a vector that we can use. With hand tracking, we need to extract the hand by cropping the camera pixels and perform geometry rejection and clamping. We then filter to stop recursive crop inflation, and we use a €1 filter to remove any micro jitter. So, speed. I want to skip unnecessary hand tracking computation. Doing so will reduce network passes to the absolute required minimum. By default, BlazePalm fires a palm detector on around 90% of frames, but this isn't necessary for our landmark tracker. Why? We need to use it only for acquisition when it sees a hand and rejection when the hand gesture changes or it falls off the camera display. We also need a 20-frame re-anchor intended to bring tracking stability. Our new detector only works on around 10% of the frames on a 30 frame per second camera. Saying it another way, 90% of the palm detector is waste processing. This is sometimes referred to as amateurization. Efficiency gains without needing to solve each and every instance. It's worth noting, BlazePalm is much more sophisticated than I'm using it for. I'm using it to reduce the workload for each clock cycle. Next, I need to bind to the classifier. Essentially, this is the step that I'm most proud of because this is the ability to pass hand gestures that semantically represent the task using intermediate math inside of BlazePalm without any unnecessary computation. At first, I used flat buffer surgery to expose the internal activation 42 tensor and effectively hook into that with classifier logic, which requires no graph conversion. You can think of this as using the BlazePalm network but earlying out. Eventually, I abandoned the second CNN altogether to take the landmark and pass those directly into a classifier which fires on commands such as turning, stop, and thumbs up. This was made as fast as possible by thresholding the landmarks into a 441-bit packed Teslin machine around 0.3 milliseconds. When the model's built, it's loaded into the GUI via a capability registry. When a model is run inside of the PyQt, it's not able to be deployed without the rules that actually run it. The capability registry runs by resolving its availability. A resolution profile, in a nutshell, is the model's capability, the artifact, and the runtime delegate, and what OS architecture. It then runs a success probe that returns true. That leads me to the future direction for physical AI and OpenPave. We could build a digital twin solution with augmented vertex block descent as an alternative to Google's Majuku. In the original OpenPave, spatial or 3D awareness was not present in any VLM solution at any speed. Computer vision needs cheaper spatial accuracy to be really useful with physical AI. While BlazePalm gives you 3D information where a VLM does not, there is still a large overhead. If this could be performed on an MPU or directly in the camera, that would solve multiple speed and accuracy problems.